In Newton's idea of space-time, time moved in a uniform pace no matter which observer was measuring time with the help of clock. But as we just now saw, that in Einstein's relativity, which is of course has been tested again and again in the experiments, we know that Einstein's relativity is correct. So therefore, the correct view of time is the span of time as measured by a clock depends upon in which reference frame you're viewing the clock. And therefore, we can think of time being malleable, and probably this was what was represented by the surrealist painter Salvador Dali in this picture, in which the clocks were shown to be limp and like soft pizza melting away. Yeah. Now, why do we say that the special theory of relativity is essentially telling us that our idea of geometry has to be extended to the full space and time manifold? Let us cast our mind back to the Euclidean geometry which we have learnt in school. Euclidean geometry says that supposing there is a point in three-dimensional space with coordinates x1, y1 and z1, and there is another point whose coordinates are x2, y2, z2, then the distance between these 2 points is given by the square of the distance is given by x1 minus x2 whole square plus y1 minus y2 whole square plus z1 minus z2 whole square. Now note, this distance doesn't depend upon what is your coordinate system which you have chosen. For example, the distance between these 2 points, which is square root of x1 minus x2 whole square plus y1 minus y2 whole square plus z1 minus z2 whole square, this distance is going to remain invariant whether your friend who has a rotated coordinate system, he measures the distance. That means what? The distance as given by the Pythagoras theorem, which is part of Euclidean geometry, is invariant no matter whether your frame of reference is rotated or translated and what have you. Similarly, Minkowski, he formulated Einstein's special theory of relativity, in which he showed that the four-dimensional distance between two events, supposing two events has occurred and one event is characterized by its time of happening t1 and its 3 spatial coordinates, and similarly other event happens at time t2 at x2, y2, z2 coordinates, then the four-dimensional distance, which is square of the speed of light multiplied by t1 minus t2 whole square minus the three-dimensional distance, this quantity, which is called the square of the four-dimensional proper distance, this remain invariant no matter in which inertial frame you are looking at those two events. This was the crux of special relativity, which said that we have to generalize the notion of distance to the four-dimensional space-time, and here the four-dimensional proper distance is somewhat different from the Euclidean distance, in the sense that if you take the sign in front of the square of time to be positive, then you have to subtract from it the three-dimensional distance, or you can say that the time part is negative and to be added to the three-dimensional distance, which is a very, very different concept which arrives. So we are now generalizing, we have gone beyond Euclidean geometry. So, in Minkowski's words, henceforth space by itself and time by itself are doomed to fade away into mere shadows, and only a kind of union of the two will preserve an independent reality. So Minkowski was essentially summarizing the geometrical notion of special theory of relativity. Now we come to gravitation. Why did I talk about special theory of relativity before I embarked on the fundamental law of gravitation? I tried to show that special theory of relativity can be cast into a geometrical language which says that the square of the proper distance, the four-dimensional proper distance between two events, it remains invariant no matter from which inertial frame you are measuring the proper distance between the two events. Einstein realized that Newtonian gravitation theory cannot be correct because in Newtonian gravity, the force of gravity acts instantaneously between two massive points. But Einstein's relativity showed that nothing can move faster than the speed of light, and therefore Newton's theory must be wrong. So Einstein embarked on his quest for a relativistic theory of gravity. But what was known of gravitation during the times of Galileo and Newton? For example, Galileo had already shown that the inertial mass of an object is equal to gravitational mass, whereby what it means is that if you drop objects of different masses from the same height, then all these objects will land on the ground at the same time. This was highlighted by his fabled Leaning Tower of Pisa experiments, from which Galileo was supposed to have dropped masses of different weights and shown to the public that all of them landed on the ground at the same instant. We should go back. This principle of weak equivalence have been tested again and again by Yotvos, by the Indian gravity experiment, which is housed in Gauri Budnoor of Tata Institute of Fundamental Research. What Einstein did was, he, as a brilliant man, he landed upon a principle which even a school kid could have thought about. What Einstein realizes that because of this weak equivalence principle in which inertial mass is equal to gravitational mass, he realized that if you want to get rid of the forces of gravity, all you have to do is go to a frame which is freely falling in gravity. That means, supposing you are in a lift and due to an accident, the cable of the lift which is suspending the lift from top, it snaps. Then the lift will start freely falling below, and then if you conduct any experiment, because of the weak equivalence principle, since everything is falling with the same rate, the inside observer inside this lift will not see any gravitational force. Everything will be falling uniformly.